We're going to do both. So on this left one, the first one, what do we have extrema-wise? Oh, I heard it. If you ever need an extra copy of a bell work, if you lost it, if you're over there on Monday, I'll keep extra for you. Just for everybody. If you ever need an extra, it's over there. Negative 1, 0 is a point. That's the point we're looking at right here for this guy. I gotta make my pen just a little thicker. So thinking about negative 1, 0, what kind of extrema is it? That's really thin. Let's try that again. Yeah, this is an absolute minimum. It's as low as it goes ever. It's never going lower than negative 1, 0. It's our absolute minimum. Do we have any other extrema on this? On that one? My turn. All right. Oh, there was the same person. Darnell? In here? I think you just went to go try this. Cool. I'll hang it. All right, let's do our end behavior on this one, and then we'll look at the other one. So our end behavior, that's describing our arrows. We can do as x goes to infinity. That one's talking about our right arrow. As x goes to negative infinity. That talks about our left arrow. We need two statements, and they can be in either order. If you do negative infinity and then positive infinity, that's totally fine. Or if you do right then left, positive then negative, that's totally fine. We just got to be careful because we want to say as x gets big, as x goes to positive infinity, where is our graph going when x goes to the right? Where's it going? Up, down, or straight to the side? Up. So how do we say that our y is going up? Thank you, dear. Schmerp. So my y is going to go to what? Infinity. My y is going to go out to infinity. That's saying that this right arrow is pointing up. That's what this whole sentence says. This says the right arrow points up. So this one says the left arrow. Where does the left arrow point? Up. So we're going to use that same second half of that sentence. Since this arrow points up, we also know that our y goes to infinity on the left side. So we describe the right arrow and we describe the left arrow. Right arrow points up, left arrow points up. Same deal on the right-hand one. I know the arrows are very, very thin. The arrows are there, I promise. So let's look at our extrema first, and then we'll do our end behavior again. Let us bounce back and forth. Mental, a little flexibility in our brain exercise. So where? My turn. My turn to talk. Where do we have extrema on this one? Ish. We're getting the vibe on it. Don't worry about decimals. Negative 2, 2 up here. Yeah. Negative 1, 2. And I understand they're not on your paper. It makes it really tricksy to see sometimes. Negative 1, 2. When in doubt, put a dot on it on your picture and it'll help you figure out if you're in the right spot. What kind of extrema is that? It's a maximum. Is it relatively maximum or is it absolute? Relative. Absolute means ever of all time. So this is a relative maximum. It's a high point, it's a mountain, but only of the nearby mountains. Where else do we have an extrema? 1, -2. A similar point. It's really important that we have those negatives in the right spot. It makes a difference because these are both 1 and 2. -1, 2 is way up here. 1, -2 is down over here. They make a difference. I know, these are the funniest of all math problems. So funny. What kind of point, or what kind of extrema is this one? It's a minimum because we have a valley here. And it's relatively minimum because we can see that it's going to go lower someplace else. So this one is a relative minimum. And then we're going to do the same deal to try and find our end behavior. End behavior. So I'm going to write that again. I don't know what that is. That looks like behavion. There we go. Behavior. I'm good at writing. And I'm really good at writing in straight lines without lines. Totally, definitely. So we want to talk about our right arrow and we want to talk about our left arrow. So I want to know what happens as x goes to infinity, as x gets really, really big. What happens to y? As x goes positive, as x goes to the right? Which way is the right arrow pointing? As x gets big, it's coming this way. Where's it going? Look at the right arrow. As x gets big, where's the arrow point? Does it come this way? More. Where? Is it going up or is it going down? Up. We're looking at this guy. As x gets bigger, as we go more and more to the right, it points up. So y is going to go up to infinity. If x gets small, if we go to negative infinity, that left arrow, what's going to happen to y? It goes negative. It's pointing straight down. It's going to go negative infinity. If the arrow points down, it's negative infinity. If the arrow points up, it's positive infinity. Okay? Questions on the belt? They're not real ones, though. Wait. They're independent from each other. I 3D printed them. But I'm a crafter, so.
Did you write them?
Huh?
You wrote them?
No, I 3D printed them. They're separated. It's just funny. I amuse myself. Okay, questions on these two? Because we did a lot of pieces here. We have found a lot of things and we have described a lot of stuff on graphs. We've been looking at graphs and taking information off of them. What we're going to do in this next bit, when we start looking at our next section in the notes, we're going to be taking the bits like we've collected, all that information, and trying to make a picture from that. So, in your notes packet, it starts like this. It's page 11 in the notes packet, and it starts with this 8.4 and then a whole list of information. Page 11, it looks like this. And this is one of those things that's from that workbook that I gave you on like the first Monday that we had. This thing that we just like never use, but it's from here, so yay, reason to And it just kind of sums up all the things we've done so far. We've talked about domain. It's which x values we have. The range, which y values, or f of x. That's what the f in me is. We've talked about our intercepts, where it's crossing the x or y axis. We haven't done anything with symmetry right now. Don't worry about that. We're kind of skipping over that one for a little bit. But we've talked end behavior, where our arrows go. We've talked extrema, our high and low points. The last couple of pieces we're going to see here that are going to be in our descriptions are going to be things like increasing and decreasing, and when we are positive or negative. And we'll see those kind of as we get working with the examples we're looking at and how we'll use it. Mostly we're going to use that for a, does this work? Great. And so what's going to happen is we're going to be given a list of information like that, and we're going to try and draw it. We're going to try and sketch it. Since we are doing some drawing, and some of them are going to be things like lines, we need some tools to help with that. So I'm going to toss a few rulers out onto the tables. You're probably going to have to share, because I have lots of rulers. I don't necessarily have 30 of them. But I have a fair few. So you will probably have to share, but we can do that. What's up? We're going to use these in a minute. I'll tell you when we need it. Because it's meant to be a flexible ruler, but it sits in the cup and then it just kind of melts. It's meant to be so that you can't like snap it, but it just winds up being kind of floofy. It's weird. That's why I saved that one for last and I try not to give it out. Schmerp. Awesome. You keep this one here. You keep this one back. All right. So we're going to look at this list of things. You can just go with your stuff. Okay. Just that will go. We've got this list of things here. We've got a y-intercept at 0, -70. It says linearity. All that means is it linear? Yeah, it's linear. Which means what's this going to look like? A line. Shock. That's why we have rulers. So this tells us right here that we're going to be dealing with a line. So we're going to use a ruler. It should be 11. Yes, 11. So we know we're going to use a ruler. Grab my ruler. We also know we have a y-intercept at -70. So we have a y-intercept where we're going to cross our y-axis at -70. So I can put a point right here. What we're going to look at now is we're going to look at when a value for x is going to be positive. So we are going to have our graph, our picture, our line is going to be positive starting when x is when x is smaller than -30. What we mean by positive, all of our values for our graph are up here. Positive is above our x-axis, negative numbers are below. It's the y values we're looking at. So when x is -30 and smaller, our graph should be above this line. Most of the time we're going to give you more information than that spot where we need it. But we're going to look here. When x is at -30, I'm going to draw a dot right here. That's where x is -30. When x is smaller, so when x is littler or more negative, my line needs to be above. My line needs to be up here. So what we're going to do is we're going to take our two dots that we have here, when our x is at negative 30 and our y-intercept at negative 70. And we're going to connect them. And we're going to use that to help us double check. So when we have a line or something that is linear, what we need is about 2 points. More is better, but 2 points is enough. And we're going to connect them up, and since it's 8 lines, we're going to use a ruler. I can't draw it on the screen because it won't let me doing it that way. But I'm going to get a line. You're going to connect them up with a line. Whenever we are drawing our graphs, I want you to go as far on the graph paper as you can. So don't draw me a little bitty graph that just goes from here to here. All the way to the edges of the graph paper. You don't have to go like all the way to the edges of the paper. I mean, you can if you want to, but we're going to go all the way to the corners of or to the edges of the graph whenever we're graphing. That gives us enough information to see what we need to see. So we're going to plot up the information we know, see what we can see, and double check with everything else. Because we have more information. We're told our end behavior as x goes to infinity, meaning as we look at the right arrow, our graph should point which way? Up or down? For right arrow. Which way is that going to point? Down. If we look at this one says left arrow. Which way does left arrow point? Up. So if we look at the picture we drew, I did wind up with my right arrow down and my left arrow up. So we can use the other pieces to help us figure out if we did it right. So we're going to plot the things we can, connect up everything we can, and see if everything else matches. When it's talking about decreasing or increasing, think about when we read things like words. We read from left to right. We'll read where the graph is above, below the x-axis instead of 6, So we read left to right. So when it talks about decreasing or increasing, it's reading from left to right. So if it says decreasing, meaning it's going down, it's going down from left to right. That's the way you read. If it said increasing, it would be going the other direction. It would be going uphill. We're not going to do tons with increasing and decreasing, but it gives us another option for how to check if we've done it right. Let's do another one because we'll get a lot more that are like this than we will of the linear ones. Let's look at another example. So we're going to sketch this. We are sketching graphs here, which means we're getting it-ish. We're getting it as close as we can, and we're not going to stress about it. So let's plot up the points that we know. We know we have a y-intercept at 0, 3. So I'm going to plot the point 0, 3. So 0, 3 is right there. So I know that part. Well, we know it's nonlinear, because that's the next thing to say. Linearity. Is it linear? No. So that just means don't use ruler. It's not supposed to be straight. It's supposed to be a little bit more wiggly, squiggly. Might be different shapes. When we say something like continuous, all that means is we're not going to start and stop. Excuse me. We're not going to have any big old jumps. We're not going to pick up our pencil anytime we're drawing. We're going to start at one end and we're going to go to the other and not pick up our pen. That's all that means. Then we're going to look at where it says positive for all values of x. What that means is you will never be down here. I could erase this part of the graph and be totally fine. We are never going to have a negative y value. It is positive everywhere. So it is only going to be above there. It's only going to be in the positive ones. Only going to be in the positive numbers. We could do what we want to do with decreasing, like I could look at that again. I'm going to show us another way that we can do this. Because the other piece of information we have here is I know that we have a minimum at 0, 3. So not only does that my y-intercept, this is also my minimum. So that's as low as my graph is ever gonna go. Ever. It's never gonna be below that. So we know this is gonna be some sort of minimum. So my graph is gonna look at least a little bit like this. Hello, wrong size pen. Because it has to give us a valley in order for it to be a minimum. Now, they don't tell us about any other relative or any other extrema, so we could have like other pieces in here where we'd have minimums or maximums. They're just not listed there, so it's probably that we don't have any. But we're sketching, so we don't have any way of knowing for sure. So if you want to get creative with it, more power to you. But we could just say it's going to do that. It's going to go up. And we can double check that looking at our listed end behavior. Or you can use your end behavior to see that if we're not sure. So maybe you're like, all right, I've got my minimum, but I don't know what's happening even higher. As x goes to infinity, so as we go to the right, where's our arrow pointing? Up. As we look at the left arrow, where's our arrow pointing? Up. Both arrows are going to point up. So this one says, whoop, wrong pen. This one says right arrow up. So we're going to have an up arrow over here. And this one says our left arrow is going to go up. So we're going to have an up arrow over here. From there, we can make our kind of guess that it's going to look kind of like that. But we're making a guess because maybe it's not a U, maybe it's a V. Maybe it's got more squiggles. Maybe it's got like wonky things going up over there. Maybe it just goes like woo the whole way. We don't know. We're getting as much information as we can and going with that. So we're going to plot the points we can. Use as much information as we need to figure out a vibe. And we're going to plot our points. Okay. We're going to practice this a couple more times because these are weird. Yes, dear. Yeah, let me write you past things again. So let's look at the next page. Here they're trying to give us a story problem contexty. Helps I find my glasses. All right, read through this little story here for a second. Because there's a lot of information in there. Here, go dear. All right, so we've got this person is thinking of buying, is test driving a car. she accelerates up to 60 miles an hour, and then she's decelerating back to zero, back to stop. So, they give us some information here. They've picked a little bit out of the story to tell us that she is starting her driving test, or her test drive, at 0 miles an hour, which makes sense. They're not going to like push the car and then try and start it. So our y-intercept is going to happen at 0. She's starting there. Then they tell us, and they help point out in our extrema here, that the maximum speed was 60 miles an hour, and she got there in 15 seconds. So what could I do with that information up onto the graph? How could we mark down that her maximum speed was 60 and she got there at 15 seconds? Where would we put the 60 miles an hour? Or how could I mark 60 miles an hour? This is a lot harder to do if you try and nap when I'm talking. Oh my goodness. So confident in our skills. Yeah. Our speed, that's the y up here. So our y is 60. What's our x going to be for that point? 15 seconds. So we're going to come over to 15 seconds. There we go, 15 seconds. And put it out here. Be careful. Follow the line. Start somewhere and trace the line. It's a lot easier than just kind of eyeballing it. So at 15 seconds, she got to 60 miles an hour. So I could mark the start of her drive. She was beginning at 0, and she got up to 60 real fast. Like she connected those two things. Like she took that accelerator pedal and just went to the floor. How fast is this thing getting up to 60? She got from 0 to 60 in 15 seconds, which is literally not very quick. Then what she did on her drive was she's like, all right, I'm up at 60 miles an hour. She wants to stop now. It takes her 15 seconds to reach her maximum speed. And then it took her an additional 15 seconds to come to a stop. So what time was it, or how many seconds had it been when she got to a stop? If she was speeding up until she got to 15, and then she takes 15 more seconds to get all the way down to a stop. 30 seconds. And how fast is she going when she stops? How fast is she going? If I'm stopped, how many miles an hour am I going? 0. So she stops here. So I could connect those pieces up, and this is how we can kind of sketch out her test drive. What they're looking at in our kind of paragraph off to the side for these missing pieces, it's thinking about how she was increasing in the beginning and then decreasing at the end. So as she was speeding up, when the car was going faster and faster and faster, we can see that she was increasing the speed. There's a big clue that said increasing right there. Hayes increases the speed. And all it means at a uniform rate is that we connected our dots. Ta-da, I made a point. And then she was decreasing her speed at a uniform rate, because we connected our dot, until she reached a stop. Because she can't just like start a test drive and go, sweet, I know what I need to know, tuck and roll. and leave it rolling down the street. She has to take the car all the way to a stop, or they're going to get real grumpy at her. So she goes until she reaches some sort of stop. But I'm just grabbing this phrase right here, and I'm just going to put uniform down here. And all that means is we connected the dots. We used a pattern to figure this out. Since she starts at stopping, like since the car was parked at the beginning, and the car is parked at the end, she is stopping at 0, and she is stopping over here. What's going on with the end behavior? Do we have arrows? Should we have arrows? Because can I take a car and make it go negative 6 miles an hour? I can't go backwards in time. I can't go from, before my test drive, let's make it go faster. I can't go before I start. So there's no arrows because it doesn't make sense in this situation for anything to go out that farther. So there is no end behavior. There's no ends. I don't have anything where an arrow is. End behavior describes the arrows. If we don't have arrows, we don't have end behavior. So if there's no arrows at all. And the last sentence in there we're trying to get us to see that is since they start at 0 miles an hour and they ended at 0 miles an hour, they're not moving. It's not going anywhere. There's no arrows. Which is just a little weird. It feels weird. And it happens. More often than not, things will look like that next one. Let's do one more normal one because the story ones are weird. We'll do this one as our last one today. Yeah. So we have a lot of pieces here. We have that it's nonlinear, so all that means is I don't need a ruler. The increasing thing, you can use it if you want to, but I'm going to start with everything else first. I'm only going to use the increasing or decreasing if I really, really, really have to, because it's just a little weird. But I have a y-intercept located at 0, -3. So I'm going to put that point first. 0, 1, 2. I've got my y-intercept right there. 1, 2, 3. I don't know why it keeps looking like it's the wrong spot, but it is. We also know we have x-intercepts at -1, 0, and 3, 0. So I'm going to put those points on there. -1, 0, and 1, 2, 3, 0. So I'm going to point right there. And we're told that we have an absolute minimum. Our minimum here is at 1, -4. 1, -4. So I need to go through the pink dot, through the green dot, through the purple dot, and to the pink dot, because we're going to go from left to right when we connect these up. So I need to make sure that we can go through here, here, and up through here. Because this is my minimum, so I'm not ever going to go below it. And if it helps you, you can absolutely come in here and say this is the minimum. Just make sure you write it below there so that we know that my graph can't go lower. That's the bottom. That's the floor. So I could take and I could try to connect some of these pieces up and say, well, I know these guys are going to connect kind of like that. That line's really thin. Because I can see through the pink, through the green, through the purple, and through the pink again, it makes kind of this shape. Let's make sure that it matches our end behavior before we kind of commit to everything. Because we know this, we say as x goes to infinity, f of x goes to infinity. Is this right arrow or left arrow? Right arrow. Is it going to point up or down? Up. So right arrow points up. Sweet, that looks good. Is this one left arrow or right arrow? Left arrow. Is it going to point up or down? Up. So right arrow points up, left arrow points up. This is looking all right. Yep, you're good to go. So I'm going to connect and just finish out my sketch here. Because it looks kind of like that. If you feel like getting artistically creative and you would rather do something, you know, woo, go for it. It's not wrong. Simplest will be is kind of like that. But you can draw your lines however works for you. It still does meet the other qualifications. This is increasing. It is getting bigger after x goes to 1. So when we get x bigger than 1, that's where my line starts going up. But that's really hard to use to help us draw. It's doable, but it's really tricksy. So we're going to plot the points we can, give as many details as we can, and connect up and anything we can't use to help draw, check and see if that's what makes your picture better. Okay? Use that as your double check. I'm going to give you guys homework 3. Oh, snap. And it's just more practice of these sketches. It is not anything more than that. We will practice doing sketches like this again tomorrow. And we'll look at some other ways of kind of using sketches and starting how we could actually do equations like this. This is homework. Yes. Homework 3, I have it marked as due on Thursday because you guys can actually do everything on it right now. We should have some time tomorrow where if you have questions, we can look at them or we can talk through stuff again or you can just ask me. You guys have about 5 minutes right now where you guys can start on this. All right, so take a look at pieces, all that jazz. Let me